We are really pleased to have Timo Berthold as our next speaker. Timo has immense experience working on solving technology for mixed integer programming. He is currently a senior engineer at CPAIOR Express, and he's also very well known for his work at the skip solver during his time at the SUSE Institute in Berlin. And Timo has published many papers on solving technologies, such as integrating constrained programming into MIP and MIP technology, and also won several awards. And he's also the main organizer of the summer school combinatorial optimization at work that is running just now, which means we also have to finish punctually today because he has some more presentations to do tonight. Before I hand over to Timo, I just want to quickly say, if you have any questions, then please post them in the chat or raise your hand. And also please mute yourself so that we can hear Timo well. Okay, and now hand over to Timo.
Okay, thanks Andrea for this kind introduction, and welcome everybody. Good evening, good afternoon, good morning. So, when I was asked to hold this masterclass on recent developments in computational MIP solving, I was wondering what to talk about. So, what are things that drive the research in this field? And I see three major motivations for research that we currently have in computational MIP these days. And even so, the Olympic Games fell through this year. I think the Olympic slogan very well describes what these three directions stand for. Citius, Altius, Fortius, faster, higher, stronger. So first, faster. Of course, improving the sheer solver speed is a great motivation for research, and many papers are published that ultimately show how you can improve performance. That's also what I did a lot of my work on. So, however, these days, a lot of this work is on very specialized methods, and it would need a lot of explanation of what the actual state of the art is in detail before one can really appreciate the value and the beauty of new developments. So this did not seem to be a really great topic for me today. Second, stronger. Another main direction is the stronger integration with other fields, hence enabling new features, making MIP solvers more powerful. There was a considerable subgroup in the MIP community that has worked a lot on nonlinearity in recent years, and that's a very interesting topic, undoubtedly. However, it seemed pretty far away from the classical CPAIOR theme, so I decided against it. And also in recent years, of course, machine learning is a hot topic, but there are really better experts than me on this topic. So I linked here a great presentation by Andrea Lodi. However, we will see one such ML application for MIP later today. So this leaves us with the third point. Finally, higher precision. This is another direction of current research on LP and MIP solvers. And I decided to talk about the numerics of solvers today because this is highly relevant in practice and only rarely covered in classes. So I will introduce a few different techniques to improve numeric stability that have been recently published and are used by state-of-the-art MIP solvers. So work on numeric stability of MIP solvers can be roughly divided into three different categories. The first one is computing exact provable optima by the use of exact arithmetic and rational number representations. This is certainly the most precise method, but at the same time often too slow to be of practical applicability. The second method is to try to boost the precision of solvers by either using higher order floating point representations like quad precision, or by applying methods that aim at increasing the number of significance bits that we can get out of our solver. We will see later what this means exactly when we introduce two such procedures towards the end of the lecture. One main challenge here is to find ways to use as few slow arithmetic as possible to keep these methods efficient. And finally, the third option is to improve the numeric stability of this standard solving method, or rather of the model that is solved directly. This can be done by taking numeric considerations directly into account in pre-solving or cutting planes, and this has been done for a long time, or by scaling the input data in a way that promises a most stable solve. And yeah, we will demonstrate this later with an example how this could work. But first, let's get everyone to pace what LPs and MIPs are and how they are principally solved. So, a linear program, or LP, is an optimization problem where we optimize a linear objective function with respect to a set of linear constraints, and all our variables are assumed to take real values. Typically, an LP is written in standard form, which you can see on the slides here. In standard form, all linear constraints are given as equations, and the variables are required to be non-negative. The set of feasible solutions for this problem defines a polyhedron, and the polyhedron is a convex set. So the fact that we are optimizing a convex function over a convex set makes this a problem that's principally easy to solve. Here, easy means that it's solvable in polynomial time. LPs with millions of variables and constraints can be solved efficiently in practice by the simplex algorithm, or also by the barrier method if you want to solve a standalone LP. And the simplex algorithm essentially performs a long sequence of matrix vector multiplications. And this is the main source for numerical errors, which are the topic of this masterclass. So note that numerical errors might occur both in the primal side, which leads to constraint being slightly infeasible, or also on the dual side, which leads to dual values being slightly negative. Hence, the solution not being truly optimal. And then integer programs are often stated in an inequality formulation and not as equations, but that doesn't really matter. You can easily reformulate the one by the other. So an integer program, or IP, is an optimization problem where we minimize, again, a linear objective function over a set of linear constraints, and we require all of our variables to be integer. And this introduces a third kind of inaccuracies. Next to infeasibilities in the constraints and negative values in the duals, you could also be faced with integrality requirements not being exactly fulfilled now. So when we have an integer program, we get the so-called linear programming relaxation if we drop the integrality requirements and only keep the inequalities. So in the picture here, you see the LP relaxation as a blue shaded area. The set of feasible solution of the IP is shown as thick dots, and the green dot is the optimal IP solution. We call that linear programming is easy because we optimize a convex function over a convex set. For an integer program, the set of feasible solution is not convex. It's not even connected. It's a discrete set. In our example, it's just 7 feasible points here. So this non-convexity is essentially what makes integer programming an NP-hard problem in the mathematical sense. And not to forget about, a mixed integer program, a MIP, is an optimization problem where we minimize a linear objective function over a set of linear constraints, and we require some of our variables to be integer, and others might just take real values. So the set of variables is partitioned into a set of integer variables and a set of continuous variables. And note that the solution set is, again, discrete now. It will be a discrete set of polyhedra. And sometimes this is also referred to as a mixed integer set. So in the example on the picture, mixed integer set consists of 4 different parts of these 4 blue lines that you see. Okay, and mixed integer programs are typically solved with the LP-based branch and bound algorithm. So this is a tree search algorithm, like you have seen many before. And there are some important details where LP-based branch and bound differs from the tree search algorithms in SAT and constraint programming. So one important difference is the use of a strong relaxation. Solving the LP relaxation considers all constraints at the same time and often leads to way more deductions than, for example, unit propagation of single constraint. So you get a real close bound on your optimal objective value typically. So, and this of course comes at a price. So processing a MIP search node often takes orders of magnitude more work than processing a SAT node or a CP node. And consequently, MIP search trees are often much smaller. MIP solvers often solve very complex problems with a few hundreds of thousands of variables and constraints within a few hundred nodes. And finally, an important difference is that MIPs usually are optimization problems and not feasibility problems. Hence, we compute dual bounds all the time to prune the search tree when it gets suboptimal. So, for a quick recap, just let's look at an example. We want to solve this problem here, which is a pure integer program via LP-based branch and bound. So first we have to select a problem to start with. So in the beginning, there's only one problem. This is just the original one. And we solve the initial relaxation. This gives a fractional solution. Here, in this case, both variables take a fractional value. So this we get from our LP. And we decide for one variable to branch on and conduct a branching, and this creates two subproblems. On the left-hand side, you see the visualization as a tree structure. So the root here being the original problem, and when we branch, we add two new leaves to a node. So we now select one of the subproblems to be solved next, and we solve the relaxation of this subproblem. This time there's only one fractional variable. We branch again, create again two subproblems, and one of them you cannot see here in the picture because it's infeasible, but it's still there. And we select one of the two subproblems, we solve its relaxation, and yay, now we find that the relaxation is integer. And this means for the remainder of the search, we don't have to consider any solution or subproblem that has a worse or equal solution value than this one. And this is depicted here. Everything below the red line is provably suboptimal. So, and then assume we selected the sibling node. Next, relaxation is infeasible, thus we can prune the node, continue the search, select the only subproblem that is left at this point, solve the relaxation, branch again, create two new subproblems, select one, solve the relaxation, integer feasible, so we update the incumbent, and now we finally have to select and solve the last node, which is infeasible again, and this concludes the search. And the current incumbent is an optimal solution to the initial integer program, just like other branch and bound algorithms, and all the time we solve in between, we solve the LP relaxation. So, as I said, note that all the time we are solving linear programs with the simplex algorithm, and we're dealing with fractional solutions. And this is where there is ample room for numeric inaccuracies. So let's talk about numeric stability and why fractional solutions are a source of errors. So all commercial solvers for linear and mixed integer programs rely on floating point numbers, which is the standard way to represent numbers within a computer. And floating point based software might generally be challenged when the problem it is trying to solve is numerically unstable. So let's try to understand a little bit the problem that comes with using floating point arithmetic. The double consists of 64 bits, of which 52 bits are used to represent a fraction, and the others are for the sign and the exponent. And if you have 52 precise bits, that's about 15 to 16 digits that you would get precisely. Hence, beyond those 15 digits, floating point numbers always consist of random noise, as you see here for the example of 1/3. The first 15 digits are precise, and afterwards, random noise. So, and this gets problematic once cancellation takes place. So, we see a very simple example. 3 million times 1/3 minus 1 million should be exactly 0. But we get a number that has non-zeros from the 9th digit after the comma onwards. And if we take this example further and go into the trillions, non-zeros already occur in the 3rd digit after the comma. So because such residual errors are unavoidable, solvers use numerical tolerances, often 10 to the minus 6. So numbers with absolute values smaller than 10 to the minus 6 are considered 0. Differences smaller than 10 to the minus 6 are considered equal, and constraints violated by less to the 10 to the minus 6 are consequently considered fulfilled. And the same for duals for the optimality requirements. So the first example will lead to numerical inaccuracies, where we got the example with the millions. The software correctly classifies the result as being 0 because the first 6, even the first 8 digits after the comma are 0. And it treats it as such internally, but if it is asked for that value, it will report a slightly off 0 value, as you see. The second case is more severe, since the solver does not recognize the value as 0. Hence, if such a computation occurs internally, it might take wrong decisions on this base and ultimately report wrong results. So, numerical stability refers to the question how prone a model is to the occurrence of such numerical errors. With this in mind, numerical stability is a really crucial topic in many applications. So as we saw in most computations, small residual errors will inevitably occur, and these might propagate and increase in magnitude in follow-up computations. For badly conditioned problems, this might even lead to wrong results being reported. So in our community blog, which is linked here, you will find a series of blog entries that I wrote on this topic and what to do against it and so on, but you will of course also learn now in this masterclass. Numerically challenging problems are common in practice. So about half of the client models that we received in the past years showed at least some indication of numerical instability. So this doesn't mean there were errors or so in these models, but at least we could measure that there was something in the matrices that could lead to slight numerical inaccuracies. So nevertheless, MIP solvers can handle almost all of these models that I mentioned gracefully. And we will also address the question why and how they can detect the model as numerical problems. So, and to analyze potential issues expressed as MIP solver, but also other solvers provide numerical analysis tools. So there's information that you get in the beginning of the solve about the distribution of coefficients in the model. So this picture from a log here shows the minimum and maximum absolute value of the matrix coefficients, the right-hand side values and the objective coefficients. And these coefficient ranges are reported both for the original model that was put into the solver and the pre-solved and scaled model that the solver actually solves. In the example on the slide, you can see that the range in the matrix coefficients could be significantly reduced by pre-solving and scaling, and which is a good thing. And the right-hand side range was slightly reduced, the objective range stayed the same. So for such a model, we would typically expect a smooth solve without many numerical issues. So as a rule of thumb, I would say if you, within single rows and columns of the matrix, you have less than 6 orders of magnitudes, and within the overall model, you have less than 9 orders of magnitudes, you're usually fine. So then there's information that you get after the solve. And this reports which kinds of numerical issues actually occurred. So in this example here, again from a log, this is pretty bad. And this is not from the same model, by the way, as above. So this is a numerical troublesome solve. And there's a rule of thumb here. A few dual failures are acceptable. So these are errors that are most frequent and do not need to be worried about. So if this is in the 1 or 2% range of dual solves, that's typically fine. And all other kinds of failures are worse and action should be taken if they occur. Okay, and to more systematically measure numerical properties of a model and a solution, there's the notion of condition numbers. So the condition number of a matrix provides a bound on how much a small change in the input might potentially affect the solution. So vice versa, this means by how much a small error in the solution will lead to an infeasibility in the constraints of the duals later. So the condition number of a full rank matrix is defined as the norm of the matrix times the norm of its inverse. And in MIP solvings, where do we have square invertible matrices? Well, that's in the basis inverse of the simplex algorithm. So computing the condition number, however, is relatively expensive. And in particular, if it should be done for every basis inverse that you ever get doing a MIP solve or doing an LP solve. So a viable alternative here is to sample the condition numbers at certain frequencies. And if you enable these features, then you will get a final report on how many basis matrices were stable, suspicious, unstable, or ill-conditioned. And from these ratios, the so-called attention level of the solve is computed. And the attention level is a number between 0 and 1, which is nice to read and interpret for humans. The higher the attention level, the worse the numerics of the problem. And as a rule of thumb, instances with an attention level larger than 0.1 deserve special attention, and often a revision of a model or the use of non-default controls or features of the solver. So, and this is what numerical information is really about. It raises awareness and tells you when you should pay attention to your model and the solution process. This is an important message here. So let's continue with scaling. So besides numerical tolerances and non-default simplex strategies, a common control to change when numeric errors occur is scaling. So in the past, I should say now, our most common recommendation for users facing numerical issues was to try scaling equals 16, which will enable a scaling method which is known as Curtis-Reed scaling. And I should maybe first say what scaling is. So scaling is a widely used preconditioning technique that's used in many mathematical algorithms, not only in LP solving. And one aim of scaling is to reduce the condition number in order to reduce the error propagation. Also, scaling aims at reducing the number of iterations required to solve a problem. So that's actually why people started to look into scaling some 50 years ago. And LP scaling in particular refers to the iterative multiplication of rows and columns by scalars. So this is where the name scaling comes from. LP scaling reduces the overall absolute magnitude of the non-zero coefficients in the matrix, the right-hand side, and the objective. And it also tries to reduce the relative difference of the non-zero coefficients, so exactly what we want. And the idea is that uniform coefficients promise a higher numeric stability because cancellation effects are less likely then. So more specifically, LP scaling often tries to bring coefficients close to 1. And coefficients in values around 1 are preferable for comparing against absolute numeric tolerances. So that's the rationale behind this. And there are two main scaling methods used in practice. So one is what we call standard scaling, or sometimes this is also referred to as equilibrium scaling. And this iteratively divides rows and columns by their largest coefficients. And then there is, as mentioned, Curtis-Reed scaling, which solves the least squares problem, which effectively minimizes the sum of the squares of the logarithms of the matrix elements plus some correction terms. So this optimized scaling method refers to the aforementioned scaling equals 16, and Curtis-Reed scaling often, but not always, helps for numerically suspicious problems. But it also tends to make MIP solvers slightly slower, and this is why it was not used in practice. At least not by default, but only on recommendation. Let us consider a little example here. So assume, say, a global pandemic forces you to work from home for 6 months or more, and you're very good at woodworking, so you set up a little home business. And in the small example here, we produce 2 items, cheap boxes with small setup costs and fancy, more profitable chest sets with large setup costs. And this is modeled in this small mixed integer program with coefficients ranging from 1 to 100. So also we see a potential basis matrix here, which has the 2 x variables and 1 binary variable in the basis. And the blue matrix here would be the basis inverse in the unscaled problem. and we would get a condition number which is roughly 245. So absolutely easygoing in practice, but we still want to see how we could have improved this. So if we now use standard scaling, the largest coefficient would be reduced to 1 in rows and columns independently, and we assume the same variables to be in the basis, we would now get a different basis inverse because of the different scaling. And curiously, it still has the same condition number. So standard scaling here didn't help at all to improve the numerics. And the best scaling would look as follows. So here the X represents the fraction of all materials to use instead of the direct amount. So this is the same problem, but with a different scaling. And as you see, the condition number improved by an order of magnitude. Moreover, if we increased the limit to 100 here, the first two cases would get, if we didn't increase the limit to 100, but if we increase the limit, which is 100 at the moment, and just moved it more and more towards infinity, the first two cases would get a worse and worse condition number, and the problem would get unstable eventually. And the last one, however, would remain unchanged. Okay, so now you know about scaling, and I promised you that I will mention machine learning today. So indeed, we use machine learning techniques to decide which scaling algorithm to use to achieve more numeric robustness. So let's look at the machine learning for MIP landscape to understand why this might be a good idea. So there have been quite a few publications in the last 10 years on using machine learning in an optimization context. I listed about 50 papers in the area that I'm aware of, and most of them even are from the last 5 years. So with this much research going on, you could expect that a lot of it can be found in MIP solvers these days. But actually, that's not the case. Only very few of these techniques are implemented in general purpose MIP solvers. So why is that? First, a lot of these publications are on specific applications and do not generalize. It's often much harder to come up with ML solutions for heterogeneous problem sets that have few common structure than for homogeneous common problem sets where the problems all rely on the same model. And further, a lot of the decisions taken in MIP solvers are of a quite complex nature. They have to follow multiple objectives, are of a very heuristic nature. Most importantly, we don't even know the correct best answer ourselves. So we don't know good labels for machine learning, for example. So think of branching. We want to increase the dual bound, but not only on one side, but on both sides. And at the same time, we would like to decrease the fractionality, enable further propagations, consider symmetry, and so on. So this is a very complex decision. And frankly, at a given note, do not really know what the best branching decision would be, since this also depends on all follow-up branches that will be taken in the corresponding subtree. So since branching is little understood to start with, it is also unclear what good features would be. Pseudo-costs, for those of you who you know what these are, clearly, so they would be a good feature for branching. But then, so to make it worse, performance variability is in the way. And all of this makes developing an ML approach to branching so challenging. And then this has to be compared to the sophisticated rules that are already in place that cover a lot of special cases and so on. So there's literally years and years of software engineering that went into the solvers and into such critical decisions. And you are trying to beat that. That's hard. Okay, but when you consider using machine learning for choosing a scaling strategy, you will see that most of these previous concerns do not apply. So first of all, the decision is not so complex. It is an either or decision between two alternative methods, standard scaling or Curtis-Reed scaling. Either apply one or apply the other. So second, we know some quite meaningful features, the numeric analysis statistics about the coefficient distribution that I've mentioned before, in the matrix, in the right-hand side, and the objective. We also know a good label, the attention level. So, and finally, up to now, there was no sophisticated rule in place, at least not in Express. There actually was no rule in place. The solver always used one of the two alternatives that we consider, standard scaling. So for me, this seemed to be a perfect conditions to start a project. So if machine learning for general MIP solvers works anywhere, then I thought this should be a great candidate. And it turned out to be. So the question to answer is whether we can predict which of the two concurring scaling methods that I've mentioned before, standard scaling and Curtis-Sweet scaling, is the best for a given problem instance. And to do so, we implemented two machine learning models, a linear regression and a random forest, and try to predict the difference in attention level between the two scaling variants. As features for learning, we chose the different statistics about minimum and maximum coefficients in the scaled matrix. And in particular, we consider the difference in the order of magnitude between the maximum and the minimum matrix coefficients, right-hand side value and objective coefficient, both for the matrix scaled with standard scaling and with Curtis-Sweet scaling. So therefore, we take the logarithm of the maximum and minimum absolute value and use the difference between those two logarithms as a feature. So we essentially get to know how many orders of magnitudes are between those two values. So, and we trained these models on more than 1,000 instances, and many of them are numerically challenging. So we choose the set to be the test set, the training set to be like this. And we made the following observation on our test set then, which again contained a lot of numerically challenging instances. So with standard scaling, the average attention level that we observed was a little less than 0.12. So that's pretty high, given that, well, many, but not all of the problems were numerically challenging. Okay. So we always used Curtis-Sweet scaling instead. The picture already improved significantly. So the average attention level in this case was less than 0.09. So that is to be expected since Curtis-Sweet scaling is known to be numerically more stable than standard scaling. So we just got this confirmed here. Yay. And however, that's not the case for all of the instances. So if we now had a perfect oracle that would always choose the best possible among the two scalings, we would get an attention level of an average attention level of 0.06. So whatever rule we come up with here, it cannot be better than this, but we would hope that it is at least better than the best of the two individual methods. And finally, this here is how our learned regression model performed. Almost as good as the virtual best. So this is the linear regressor, and we were quite happy with the performance. The random forest actually was even a tiny bit better, but we decided to implement the linear model nevertheless. So this has a couple of reasons. So it is easier to implement and maintain. It comes with the added advantage that it is interpretable, and we clearly see which features have much more, have the most impact on the prediction. So, mission accomplished. You can use machine learning to choose a scaling in order to reduce the observed attention level. And by the way, the computational experiments carried out for this study involved the usage of 3 permutations, for instance, for those of you who know what this is about. And the statistical test confirmed that this improvement in attention level is indeed significant. So, but what about other performance measures? The attention level is an indirect measure, but we saw different types of actual numerical errors that can occur before. So the reassuring news here is that all of them improved significantly when using automatic scaling. We got a lot less dual failures, primal failures, less singular inverts, and as errors that occur in the simplex algorithm, and also less instances where incorrectly reported infeasible, or ended up with solutions that violated the original constraints. And the number of inconsistent results, hence cases where different permutations led to different answers, was reduced as well. So note that this test set here involves many instances with horrible numerics. So all of this is not a typical behavior that you would see of a MIP solver, but rather one on these exceptional bad cases. So, and performance-wise, we observed a 10% improvement on our simplex sets, which is a great achievement. And on our MIP performance set, this change was roughly performance neutral, which already is good, given that Curtis-Reed scaling is known to be slower on average. And the fact of it being performance neutral can be explained by two effects that cancel out. So the individual simplex solves get faster, but solves generally use more node on average, which is, as said, typical for Curtis-Reed scaling. So to conclude this part of the presentation, this project has convinced me personally to consider ML for MIP more often. So my take on this is that ML in this context, machine learning in this context, works best for categorical decisions where you have a non-trivial set of suitable features in mind and an established label that connects to the features, and you are not fighting uphill against the method that has been fine-tuned over many, many years. So in the example that we saw here was learning to scale a machine learning model that predicts a best suited scaling method. It's one of many recent components in Express that address numeric stability and make it a robust solver. And we will quickly see some more of them. Forgot to forward through my slides. And finally, to really conclude on this, here is a little sneak peek of a new unpublished project on numeric stability, again using machine learning techniques. Here we try to learn the attention level directly after having solved the initial AP relaxation, and will warn the user if we predict that the solve might become numerically unstable. Herefore, we use similar features as in learning to scale, plus a special conditioning measure that is easier to compute than the condition number. So in our tests, we achieved an accuracy of 95% in the predictions. So we balanced the thresholds such that we are more likely to get false positives and the warning for instances that are not as bad as false negative, hence a missed warning. So consequently, the false negative rate is even less than the average error rate, which is a good thing. So this feature is planned to be released with the next Express version, but of course, as always in software development, nothing is set in stone until the final binary for this is built. So, but what can we do if the best scaling doesn't help because the problem is intrinsically numerically difficult? We get solutions that have primal or dual infeasibilities beyond what we would be willing to accept. So this is the task of solution refinement, and let's see what this means. The goal of solution refinement is to reduce different kinds of infeasibilities. There can be primal infeasibilities, hence slight violations of the constraints, or dual infeasibilities, hence slight violations of optimality conditions, or inequality infeasibilities, hence slight violations of inequality requirements. And these are due to numerical errors on the one hand, but also to the usage of numerical tolerances on the other hand. Naively, such infeasibilities can be handled by applying additional simplex iterations with tighter tolerances and or higher precision. So that's already one first refinement procedure. So alternatively, there are also other more sophisticated refinement procedures. So let's now look into them. So assume we solve a linear program with a double precision floating point solver. Both the primal and the dual solution will almost always have some errors. So as you saw, this can be inevitable as simple fractions like 0.1 cannot be exactly represented. And as we mentioned before, double precision solvers typically try to solve a piece up to a certain relative accuracy. If all feasibility and optimality checks pass with a relative error of less than 10 to the minus 6, the solution is declared feasible and optimal. The rationale here is that the slight erroneous point is close to the true optimum, and that's almost the same objective value. So we should be good with accepting it. So, however, there is another interpretation. So the point, this slightly erroneous point that you see as a blue point in the upper picture, is truly feasible and truly optimal for a slightly different problem. A problem that has been perturbed by the residual errors that we got from checking our solution. So it might seem a little bit like nitpicking, but this slightly different view offers some important insights. So firstly, it still holds true for ill-conditioned problems, as you see below here, where we have an objective almost parallel to a constraint. So the erroneous solution here is a solution to a slightly perturbed problem. Even so, in this example, this solution is really far away from the true optimum, but you only had to perturb the problem slightly to make this a true optimum. So furthermore, it gives us the insight that we could set up a residual problem that now describes this difference between the original problem, P, and the perturbed problem, P tilde, and solve this residual problem to improve our accuracy. And exactly this is the idea of iterative refinement. So iterative refinement works as follows. We firstly solve the original problem in fast double precision. So that's what we always do. Then for computing the infeasibilities, we use a slow arithmetic. So in the original publication on this was even an exact arithmetic. What we do internally in Express is that we would use quad precision, which is much more accurate than double precision. So, okay, so we compute the infeasibilities in this slow quad precision, and note that we, as I said, we could use exact arithmetic, and the important point here is that since there are only two matrix vector multiplications, so there's not much work, even with the slower arithmetic, we would get a relatively fast answer to this. So, and now knowing the violations in our higher precision arithmetic, we can set up a residual problem, which we then again solved in fast double precision. And this gives us correction terms to refine the previous solution that we got. And this procedure can be iterated and iterated, hence the name. So with this procedure, we can get a high precision solution while only doing very few computations in high precision. So this is really neat. Okay, so within Express, as I said, the quad precision variant of iterative refinement is implemented, and it allows to get high precision solutions with a small overhead. So the original implementation even used exact arithmetic for the checking stage and came to a similar conclusion that there is an average slowdown of 7% when computing 50 precise digits and 90% when striving for 250 digits. So, however, going the full way and getting a provably exact solution, which ultimately might require performing some keywords of the simplex in exact arithmetic, still can take a factor of 10. So this procedure here, if applied in practice, really aims at high precision solutions. And yeah, finally, in the last 1 or 2 minutes or so, I would like to introduce the idea of MIP fractionality refinement. So let's start with a motivating example of a MIP with a simple variable bound constraint and its scaled counterpart where the row has been divided by 10 to the 6th to make the largest coefficient equal 1. So recall here that exactly this is the idea of standard scaling. So the number 10 to the 6th here, of course, has been chosen on purpose since this exactly correlates to the relative tolerance of 10 to the minus 6 that many solvers use. So let's see how several solution candidates behave here. So first of all, solution candidate 1, 0. So this is feasible with respect to tolerances in the scaled problem. It only violates a constraint by 10 to the minus 6, as we just said, which is barely acceptable, but would still pass the tolerance check. However, if you port the solution back to the original, you would get a row 1 less or equal 0, which is clearly infeasible. Consequently, a MIP solver would probably report 1 and 10 to the minus 6. So as a solution candidate. So this is feasible with respect to tolerances in both the original and the scaled model. It passes both checks there, has a slight violation in the integrality. So in many cases, this would be acceptable, well, even the user expected solution for such a problem. And the common pitfall in certain applications is that people would fix integer variables to exact integral values and resolve the corresponding IP. And this now would bring us back to the first case. So, but this also means that you, if you do such a thing, fixing integer values to exact integral values, which is of course fine to do, and fine to ask from a solver, this means that you require integrality requirements to be fulfilled with zero tolerance. So, and if that is the case, then the only acceptable solution to this problem is 1, 1. So this is exactly feasible. And again, I forgot, sorry, apologies for this. So I forgot to skip through the slides. So here is C, just what I said, the 3 different candidates. One is feasible in a scaled problem, but infeasible in the original. The other one, which is slightly fractional, is feasible in both. And the only truly feasible solution is 1, 1, the third one. Okay, last slide. So the idea of fractionality refinement tries to enforce exactly this. Get zero tolerance, exactly integral values for integer solutions, while still allowing tolerances in primal and dual feasibility. So this circumvents the need for exact or even higher precision arithmetic, since you can integrate the refinement procedure within the standard branch and bound search. So what's this done? Firstly, one can explore dual degeneracy and heuristically try to come up with alternative optimal solutions where there are no, or at least less, integer variables in the IP basis. So this can potentially be achieved by additional pivots. And the idea here is if a variable is not in the basis, then it will be exactly at its bound, which is integral for an integer variable. If this does not help, one can perform additional branches on integer variables that are integral within tolerances, but not exactly integer. So there's another heuristic shortcut which might help in some situations. So performing the aforementioned fixed and reoptimize. So furthermore, this will also ensure that this will be always possible for the return solution. And computational experiments showed that this procedure gets rid of almost all the fractionalities with only a moderate change in performance. So it should be noted that this does not show the real full picture here. So there are many instances which are not affected by this at all. And obviously there are some instances which struggle with fractional solutions, and those will show a larger performance deterioration than the average change that's shown here. Okay, so this finishes my 3.5 different recent ideas that have been come up to improve numeric performance of MIP solvers. And I would like to say thank you, and I'm happy to take any questions. I see there are already a few ones in the chat.
Thank you very much, Timo. That was really interesting. So let's move on to the first questions. Do you want to read them out yourself? You can see them.
I can see them. So do we have a sense of which properties make standard scaling or Curtis-Wheat scaling the better choice? Well, not in the sense that I could say this particular problem class, but I think Curtis-Wheat scaling in particular shines for problems that have show this property of having very large coefficient distributions in the matrix. Anything that has big M formulations in there is a good candidate for Curtis-Wheat. And Another question regarding the geometric view of constraints is noting snap rounding, as it is often used in geometric algorithms for robustness useful in MIP or LP solvers. Are subnormals a problem? And if so, do you do anything to handle them? Well, I mean, there are various rounding procedures in place, and I've mentioned this on the very last slide, that one thing that you can try when you aim for exact integrality is that you just could try to enforce this and then solve the AP again, and if you would get a feasible solution out of this, then that's going to be fine. So procedures like this can be applied. So could you please clarify, how do you know that the numerical problem happened? For example, a dual failed due to numeric reasons. So yes, I mean, we get these out of the LP solver. So if the dual simplex algorithm reaches a point where it can't, where it's slightly infeasible and can't find an improving variable to pivot into the basis, and can't reduce these infeasibilities any longer, then at one point you would declare it a dual failure. Actually, what you would do internally then is try primal simplex as the next case, and if the same things, in many cases this helps to recover. Actually, if the same thing happens for primal, you would speak of a primal failure and so on. And the same thing for the basis invert. So you bring a variable into the basis, so you were expecting that the resulting basis matrix has a full rank. This is what your linear algebra beforehand told you, but then when you do this, it turns out that the basis matrix is singular, and in this case, essentially, this then is clearly a numeric failure. And what you would do in this case is that you recompute the factorization of the matrix. So would it be possible for MIP solvers to produce checkable proofs as SAT solvers? Yes, there is work on this. So first of all, the one part that I did not really cover in the presentation today is going in this direction. So doing exact MIP solving, this is definitely a requirement for this. And then the next good question is what would be an exact proof? So essentially, for LP, the proof that you provide is the dual solution. So naively, if you do LP-based branch and bound, the proof of optimality that you get is the full set of dual solutions of all the leaf nodes in the branch and bound tree. And then if you dig further into this, then you have to consider how you can incorporate things like moment propagation, cutting planes, and so on in this reasoning. So that's really for an exact proof of optimality. Proofs of feasibility, if that was the question, then this is of course much easier. Could you please repeat the features that I used to train the machine learning model? So yes, those were the, so you might remember that in the beginning I showed that the solver will report for 3 different things, for the matrix coefficients, for the objective coefficients, and for the right-hand side and the bounds of the variables, the minimum and maximum absolute values that you observed there. And the features that we used was that we used the difference in orders of magnitudes for each of these things. So, are there papers on the proof format available? Yes. If I'm not completely mistaken, then one of those that I linked for exact MIPS solving is exactly this. And you see I had way too many slides. I should probably start scrolling through them from the beginning. Somehow my laptop is a bit slow with going through those slides. One more. Yeah, the second one. IP certificates or exact integer programming. When progressing towards using more machine learning, how safe do you feel about the training data sets reflecting end user usage? Isn't there a lot of potential biased, non-balanced data set which effects might be amplified by machine learning based tunings over classic handcrafted algorithms? Yeah, generally a very fair point. I mean, we as a company are in a lucky situation that we have lots of data sets from end users and in particular from users that will use exactly the software that we are working on. And this is what we then, I mean, a selection of those is then what we use for training and testing. Which might mean that in the end the solver gets biased to the users of the express solver, but yeah, from our point of view, of course, that's fine. And I think also from a scientific point of view, the question that we raise is always fair, and the answer is just use as big a data sets as you can get. And I think here the MIPLib, in particular the last version of the MIPLib, where the collection set, as it is called, has more than 1,000 instances. And this is a good step in that direction. I believe I answered all questions, Andrea. You agree?
I think so too, yes. Are there any more? Well, it doesn't look like it. Thanks a lot again, Timo, for this great talk. And let's all unmute our phones and give Timo a clap, huh?
Thanks a lot, everyone. Thanks for being here. And yeah, have fun with the remainder of the of this masterclass. I won't be able to see it. I'm off to combinatorial optimization at work. Okay. Thanks, everyone. Bye-bye.
Bye, Timo.